All right. I'm back. So what I want to do is I need to check that we have the correct the YouTube. Where's the YouTube? This is the YouTube. 1, 2, 3, 4. Have the
One,
correct
two, three,
the
four,
YouTube.
five.
Okay, if we have the correct the YouTube, let's just check notifications. So Michael Beverly uploaded the majority report, some data, selects clips upload Russia after the Soviet Union. Teaser tells upload. I don't see anything interesting. Let's see the homepage. The homepage. What do we got? Is space-time real? Space-time. No, it's not. Teenager stabs mom 1 year after shooting father in self-defense. Yeah. Hamas favorite Drew the Gideon Levy story. Is this guy like the ultimate Judenrat? This guy is like the ultimate leftist or something? The distorted Fourier transform in some applications. She just saved both of her children. Oh, there's a line there. What's bigger? Okay, I don't see. The dog watching TV is hilarious. Hilarious. I told you those guys were hilarious. I told you those guys were hilarious. Where is that? I told you those guys were hilarious. Wait, I can't find it? It doesn't just show up? What happened? Oh my god, she just broke her nose. No, that's not real. Trump in prison causes epic meltdown. Okay, so I can't find it. I told you those guys were hilarious. What is that? Jesus. So we can't find it. Where is I told you those guys were hilarious. This is Jabba the Hutt birthday party. Let's see if this is the right one. I don't know. Is this the one? Probably not. Jedi party. But where is Jabba the Hutt's? Anyway, I can't find it. Wave equation in 2D rectangle.
A snare drum. All right, Murph. Murphy's barking here. A snare drum. And so that's a very thin membrane that's stretched over a ring. And so it can come down here.
Well, looks like James Webb Space Telescope discovered yet another unusual galaxy. A galaxy that you can kind of see.
Kind of. This guy's always kind of, potentially. He never takes a position. It's always kind of, maybe, but. Anyway, I can't find it, so we'll find it some other time. Let's see what else.
Let's just
Deriving Schrodinger's equation using A-level mathematics in 21 minutes. It should take, I've seen a 7-minute derivation. You shouldn't need 21 minutes. It should take 7 minutes, and it's really very straightforward. There's nothing surprising about Schrodinger's equation. He assumed that he took de Broglie seriously. It all starts if you assume de Broglie seriously, that the electron is waving around the nucleus of the atom. You assume that, and so you start from a wave equation. Then you add the de Broglie formula and energy formula, and I think that's basically it. Retired off Apple stock, then revolutionized physics, living in Hawaii.
To my utter shock and amazement, and just my whole brain just was electrified. This whole algebraic structure that I had been playing with fits inside this largest simple exceptional Lie algebra, E8, complete with this triality symmetry relating the generations.
I have no idea what he just said.
Thanks for joining us for.
Everyone, this is a 5 p.m. up. Everyone, this is a 5.
What would it take?
Why Lebanon will win. Israel's killing spree expands to Lebanon. Why Lebanon will win with Gadi Francis. Lebanon will win? Did Lebanon declare war? Or is it Hezbollah, which is a terrorist organization acting out from Lebanon, attacking Israel? This is nonsense. Open forum for hating Jews. That's good. Almost Gaussian. Can you solve? What do you mean almost the Gaussian? Walking in Gaza before war. Heat equation in 35 minutes. How to solve the heat equation?
Hey guys.
I
Hi
quit.
friends, welcome back. So we have some big news in the world of AI regarding the company OpenAI, which is the hottest company going. Their CTO is leaving. So I want to go through the details of this stuff and let's jump right in. So it says here is the headline. OpenAI CTO, so that's the Chief Technical Officer, Mira Murati, says she will leave the company. And she's out, guys. This is pretty insane, actually, because you guys know this. If you follow any of this, the YouTube financial verse, or you follow what's going on Wall Street, everything is about AI, right? And so why would someone, essentially one of the top people, be leaving the hottest company out there? Let's see what she has to say. I want to go over it, and I want to hear your thoughts. I'll share mine as we go through this together. Again, this is from Mira Murati. She just posted this a few hours ago. Hi, all. I have something to share with you. After much reflection, I have made the difficult decision to leave OpenAI. Again, this is the Chief Technical Officer. My 6.5 years with the OpenAI team have been extraordinary privilege. While I'll express my gratitude to many individuals in the coming days, I want to start by thanking Sam and Greg for their trust in me to lead the technical organization and for their support throughout the years. My initial reaction to this, 6.5 years is not that long, actually, for a company, right? You'll hear about people like working for 20 years for companies, these kind of things, especially, again, this is the hottest company out there. Why are one of their key people leaving? Let's see what more she has to say. She says here, there's never an ideal time to step away from a place one cherishes, okay? So she says she likes it, yet this moment feels right. Okay, our recent release of speech-to-speech and OpenAI of 01 mark the beginning of a new era in interaction and intelligence. Achievements made possible by your ingenuity and craftsmanship. Huh. It's like it's a big moment that they go in speech. They got this new thing coming out. So I guess she had to finish whatever she's working on, then leave. I guess is her claim. We didn't merely build smarter models. We fundamentally changed how AI systems learn and reason through complex problems. We brought safety research from the theoretical realm into practical applications, creating models that are more robust, aligned, and steerable than ever before. Our work has made cutting-edge AI research intuitive and accessible, developing technology that adapts and evolves based on everyone's input. This success is a testament to our outstanding teamwork and is because of your brilliance, your dedication, and your commitment that OpenAI stands at the pinnacle of AI innovation. Okay, so just we're gonna keep on doing it, but just initially, she's only been there 6.5 years. I don't think it's that long. Kind of sounds like to me she's sort of finishing a project. I don't know if there's any particular reason why she's leaving. As we go through this, let's see what she says. She says, okay, here it is. I'm stepping away because I want to create the time and space to do my own exploration. So maybe she doesn't feel that she's free at OpenAI to do what she wants, I guess. That's what she says. I'm stepping away because I want to create the time and space to do my own exploration. For now, my primary focus is doing everything in my power to ensure a smooth transition, maintaining the momentum we've built. Interesting. So there's not a lot of description of why she's leaving other than she wants to create the time and space to do her own exploration. That's her words. We'll see what she says here. I will forever be grateful for the opportunity to build and work alongside this remarkable team. Together, we push the boundaries of scientific understanding in our quest to improve human well-being. While I may no longer be in the trenches with you, I will still be rooting for you all. With deep gratitude for the friendships forged, the triumphs achieved, and most importantly, the challenges overcome together. Honestly, guys, this was like a weak explanation to me. That's my initial reaction because you're kind of like, okay, what's going on? Why are you leaving? But you can't really say anything bad, I guess. I mean, you guys know how this stuff is. It's all public. Sam Altman, so he's still there, of course. This is his response. I replied with this, Mira, thank you for everything. It's hard to overstate how much Mira has meant to OpenAI, our mission, and to us all personally. I feel tremendous gratitude towards her for what she has helped us build and accomplish, but I most of all feel personal gratitude towards her for the support and love during all the hard times. I'm excited for what she'll do next. We'll say more about the transition plan soon, but for now, I want to take a moment to just feel thanks. Okay, so they're not indicating like any hatred or anything like that. I mean, who knows? I saw someone post this picture on over on X where I guess a couple people left already, and I guess there's just 2 left. But then someone was saying one of the guys is on leave right now. This is according to Bloomberg. It says here, her departure makes the latest executive exit at the company since Altman's ouster. If you guys remember, there was this whole rigmarole just a few months ago where they fired Altman and they have disagreements with the board, and it seemed like the crux of the disagreement was the direction of the company. Basically, are we going for profit or not? Right?
Right, they're not for profit. She's not making she's barely making a salary.
What's our focus here? Are we jumping in bed with Wall Street? Are we jumping in bed with the Saudis? Like, are we jumping in bed with Musk again or whatever? Is this about money or not, or is it about research, right? Because it can go 2 different ways. And I can't speak for everyone who's leaving. I'm saying I know that was one of the things that was up in the air. OpenAI. Another thing that we up in the air OpenAI is, are we addressing safety concerns? Are we addressing sort of legal concerns? There's a lot of issues that have yet to be sort of determined at these kind of companies. So these are the people that have left. You have Ilya Sutskever, so that was the company's chief scientist, left. In May, it says, in August, co-founder Greg Brockman said he would go on leave until the end of the year. Okay, so maybe that person comes back, who knows? Then you have researcher John Schulman left for AI rival Anthropic. Okay, so you can go to a competitor. And then it says departures leave only 2 members of the OpenAI's original founding team at the company, Altman and then Wojciech Zaremba. I want to point this stuff out, guys, because oftentimes, again, in the finance YouTubeverse or Wall Street, whatever, people talk about AI as being the beginning. If this is the beginning, why are people leaving? Now, to be fair to OpenAI or to AI, it said that one person did decide to go leave and do their own company. So you can make the case that there's so many out there. I'll just say this: Altman's been trying to raise money like crazy regarding this stuff, heading out to the UAE. Right, there's something here. I'm talking like billions, trillions of dollars kind of stuff. They've been pitching, AI and things like that to the Saudis. I'm bringing this stuff up because I want to understand like how much money is in this stuff. The Saudis have also been talking to our friend dear Elon. Right, so there is money in these things, but the question is how much and how quickly will these things be adopted by industry or whatever. Now, I know it all depends on what you work in your neck of the woods, because some people in our community actually do use this AI stuff already. I've used ChatGPT, right? Because when it first came out, it was all the rage. I had to look at it. But I don't know, is it like $20 a month? I don't even know, because I don't really use it all. I'm fine with Google for my needs. I think these days a big problem, and I say problem, is that many students, say high school, college, etc., are now using it to write papers and do all kinds of stuff. And so, as a professor these days or teacher these days, imagine having to deal with that with your students. I'm sure it's a huge hassle. And then Apple is rolling out their new software and hardware, etc., to use the basically these robot things that can write text and emails for you, that kind of stuff. But I think I'm saying those use cases. I think one of the big things for me when we're talking about this stuff, though, is that when we talk about AI, it's kind of misrepresented. It's not like the AI is in the sense of artificial intelligence, in the sense of like the robots are, have free will, thinking for itself and stuff like that. Like the way these things work now is it often, copies, be it other writers out there, or copies art and kind of mishmashes it together. I think there's a lot of legal concerns with this stuff. I'll give you some examples here. So, it's been.
Yeah, this guy does not understand AI. If that's what he thinks.
An issue where.
But that's no surprise. No one understands AI, basically, as far as I know.
In Hollywood or otherwise, they've been, questioning which works are you using copyrighted stuff like that. I remember several authors had sued OpenAI, and newspapers sue OpenAI as well. Because I'll give you a simple question.
Yeah, as far as he's concerned, AI is just a copy paste. It's some automatic copy paste. That's all. It just creates a mishmash. Yeah.
For example, Scarlett Johansson sued for using her voice. I'll give you an example. So, say ChatGPT wants to get into the world of stock quotes, for example, right?
He's only seeing the bad. He's only seeing the half empty cup, glass, whatever.
The question, would be like, what's the best stock in the market? Like that's kind of the natural question you would ask OpenAI. Like, what's the best stock in the market? No, it's this one, it's that one, right? That kind of thing. Or tell me the best value, because like, for example, best stock has a kind of a connotations on there. If I say like, what's the best value, based on say P, something like that, that's sort of an interesting one. Like you have access to all that said data. I just give one example. There's multiple things that you could ask OpenAI. One of the issues is you don't know where the information is coming from. So that's a big issue. And then again, like I said, using Scarlett Johansson's voice. And there's a lot of money in this stuff.
Yeah, you don't know where the information comes from. So yeah, it's terrible. Yeah.
And I want to mention too is with the Sam Altman thing. I personally, from what I know about the guy, I've never met him personally, but I don't particularly like him. And I don't know if among young kids these days, if
he doesn't like him, so that's all he's got. Like, let's talk about the fact that I don't like Sam Altman. Why don't you like Sam Altman? How's this? Wait, like, what kind of an analysis? This guy's supposed to be a financial guy. What kind of a financial analysis is this?
If they feel like Sam Altman is like this, white knight, golden savior, AI messiah, AI Jesus, if you call him. I don't know how young kids think about Sam Altman. I don't particularly like the guy. I don't know. To me, he comes across
What? Who analyzes anything like this?
as kind of sleazy and just a money grubbing kind of person. And he's very rich doing that. Sure,
What?
I get that. But I can't speak to the other members of I can't speak to Mir. I don't know Mir personally. These kind of things. But it's interesting though. When
That's all he's got. Ad hominem. Let's just talk about the person. Let's not talk about the content, the engineering, the revolution, the product. No. We're gonna talk about what I feel about this person. That's all he's got. This is a financial channel.
when everyone's trying to pitch you that this is the start of this AI revolution, and you got people already kind of deserting the hottest company out there. There is a investigation.
That's all he's got. Let's talk about the fact that people are deserting this company. She probably has an offer, a better offer from somebody to probably create her own thing. There's already investors, like everyone that works at this firm at OpenAI probably has investors lining up ready to put billions of dollars behind each and every worker probably in OpenAI. So she probably has, I don't know what numbers we're talking about, but probably billions of dollars ready to invest in her firm. So she's doing the right thing and she's leaving. There, solved it for you. Anyway, this guy is a complete waste of time. He hates Elon Musk. 1 second. I have a message. Mm-hmm. Anyway, so let's continue. Yeah, this guy's a waste of time.
I recently came across an interesting interview on X Twitter with Yuval Harari about how our future with AI might look like.
Yeah, I don't want to hear about Yuval Harari. The guy doesn't know anything. Why do...
Welcome to this video. So in the last video we looked at Schrodinger's equation.
1 second. Okay. So we wanted to finish this. Let's try finishing this. One second. Okay, let's see what we got. So the total energy is the number of modes times the average energy. My God. One second. All right. So total energy is equal to the number of modes times the average energy. I guess this is average energy per mode. This is what has to be. So total energy. So this is average energy? I don't get it. I don't get it. Total energy. This is average energy. Average energy is KT, but this is he said this is the potential and this is the kinetic. You can't learn anything like this. This is impossible. You just cannot learn this way. This is useless. It's just useless. You can't learn. You can't just take a lecture and learn it. It's impossible. There's more questions than you have than you get answers to. This is completely useless. This is completely useless. You don't really get a feel. I'm not getting a feel. I'm just, barely understanding what's going on. I don't know what to say. Let me put a link to everything. I don't know what to say. This is like a complete waste. Not a complete, but a really big waste of time. I don't know. Each degree of freedom has equal 1/2 kT amount of energy. All right. So this is what degree of freedom? Potential and kinetic are 2 degrees of freedom. This is not average energy. This is total energy. Average energy is kT. This is average energy? How is this average energy? Of what? I don't know. I have no idea. I just have to give up. I just have to give up. It's just a complete waste of time. Total energy is the average energy times the number of modes. I mean, this I understand. The number of modes times the average energy is the total energy. Sure. But KT is the average energy? Why is KT the average energy? If you could say, I don't know, the number of modes times the average energy? I don't know. Average energy per mode. The average energy of each degree of freedom has equal 1/2 kT. Oh, you know what? This is per mode. So each mode, each degree of freedom has 1/2 kT in potential, 1/2 kT. So each degree of freedom has kinetic and potential. So each degree of freedom has kT. I don't know. Because the question is, where does 1/2 kT come from? This is the equipartition energy principle. So we need to go to the equipartition energy principle. All they're going to say is each degree of freedom has 1/2 kT amount of energy. That's each degree of freedom. But over here, you're saying that the kinetic is half and the potential is half. So each degree of freedom has kT. You just said each degree of freedom has 1/2 kT. This is amount of energy. This is average energy. I just don't know. We need to look into the equipartition energy principle. equipartition of energy principle or something. Let's try that. I don't know what else to say. The equipartition of energy principle. Equipartition of energy principle.
In this video, we're going to review the equipartition of energy principle. Okay, in prior videos, we have introduced the first law of thermodynamics, which is simply a way to do the bookkeeping of energy in any particular system. Okay, so that first law of thermodynamics is that the change in internal energy of the system is just a balance of the energy transfers work and heat.
I don't know what he's saying.
We are now going to discuss something important called the equipartition theorem. But before we do that, we need to define it.
No.
The principle of equipartition of energy is a very important concept in physics because it helps us.
So I've heard one of a previous lecture by him, and I really liked it. So maybe he's good. This is from 10 years ago. Jesus.
The principle of equipartition of energy is a very important concept in physics because it helps us explain why certain ideal gas systems composed of more complex molecules have more internal energy than less complex systems. So let's begin by examining the simplest type of gas molecule known as a monatomic ideal gas molecule. A monatomic molecule is simply a molecule that is composed of a single atom, as shown in the following diagram. Now, we know from the previous results that the internal energy of such a monatomic ideal gas system is given by this equation. So the product of 3 divided by 2, n, which is the number of moles of gas, r, the universal gas constant. And
so the reason is because we have 3 directions of motion, but for each one, it's 1/2 nRT. This is from PV equals nRT. So PV is equal to nRT. So here's nRT. And PV is energy. So PV equals nRT. But why is it divided by 2? I need the previous lesson. What's the previous lesson? Facebook, Jesus. I think there should be. This is the about website video link. Maybe from the website video link we can figure out the playlist. So this is back and this is forward. So this is the molar specific heat.
let us recall that the specific heat of a substance is simply the quantity of energy that is required to raise the temperature of 1 kilogram of that substance by 1 degree Celsius. Now, for solids and liquids, the specific heat values changes only very slightly with changes in pressure and volume. So that means for solids and liquids, the specific heat does not depend on the type of process that our solid or liquid is undergoing. The specific heat only depends on the type of substance that we're using. However, for gases, the specific heat does in fact depend on the change in volume and pressure. So it does depend on the type of process that we're using. Now, before we look at the difference in the values of the specific heat for different gases undergoing different processes, let's define the molar specific heat. The molar specific heat of a substance is simply the quantity of energy that is required to raise the temperature of 1 mole of that substance by 1 degree Celsius. And the relationship between the amount of energy and the change in temperature is given by this quantity, this equation. The Q, the amount of energy transferred, is equal to the product of N, the number of moles, multiplied by capital C, the molar specific heat, multiplied by change in temperature. Now, we just said that for gases, the specific heat depends on the type of process. So what that basically means, if we have 2 different processes for the same gas undergoing the same change in temperature, the C values, the molar specific heat values, will be different. So for example, let's suppose we have an isobaric process. In an isobaric process, our molar specific heat is given by the following variable. So Cp is the molar specific heat for our process in which there's constant pressure. And let's suppose we have an isovolumetric process. In an isovolumetric process, the volume remains constant. So that means our value for molar specific heat given by Cv will be different than this value, Cp. So Cv is the molar specific heat for an isovolumetric process in which the volume remains constant. So if the number of moles is the same and the change in temperature is the same, that means whichever one of these quantities is greater, that implies that the amount of energy that is transferred is also greater. For example, if Cp is greater than Cv, Qp will be greater than Qv, and likewise, if Cv is greater than Cp, then that implies that the amount of energy transferred in the isovolumetric process will be greater than the amount of energy transferred in the isobaric process. So let's actually explore this question. Let's compare the values of Cp and Cv, and let's try to determine which one of these values is greater. So let's begin by assuming that we begin with the same ideal gas. So the same ideal gas is heated under 2 different processes. In both of these processes, the temperature increases by the same exact quantity, by the same exact amount. So let's begin with the isovolumetric process, and let's try to determine the amount of work done by our ideal gaseous system in an isovolumetric process. So in an isovolumetric process, the change in volume is 0. So we begin with the work is equal to the integral of dW, the infinitely small change in work from position 1, from initial conditions to position 2 to final conditions. And this is the same as this quantity. Now, because our dV, because our change in volume is 0, our infinitely small change in volume is also 0. So basically, because this quantity is 0, this entire work becomes 0. So in an isovolumetric process, the work done by our ideal gaseous system is equal to 0. Now, recall that the first law of thermodynamics states that the change in internal energy of our ideal gaseous system is equal to the sum of the work and our change in energy due to heat. So because our work is 0, that implies this quantity is 0. So our change in internal energy of our system is simply equal to the amount of energy transferred as a result of a difference in temperature. And the V simply means that we're dealing with an isovolumetric process. So let's call this equation I. And let's move on to the isobaric process. In an isobaric process, we have change in pressure is equal to 0 because the pressure is assumed to be constant. So we begin with the same exact formula. The work done in an isobaric process by our gaseous system is equal to the integral of dW from 1 to 2. This is the same thing as the integral of the product of P and dV from V1 volume 1 to V2 volume 2. Now, because the pressure is a constant, that means that we can take that out and integrate, and we get the following result. The pressure multiplied by V2 minus V1, or equivalently, pressure times change in volume. So in an isobaric process, the change in internal energy is equal to Qp minus W, and W is this quantity. So minus P multiplied by change in volume. So we can rearrange this equation and solve for Qp, and we see that Qp, the amount of energy transferred as a result of a difference in temperature between the surroundings and the gaseous system in an isobaric process, Qp is equal to the sum of the change in internal energy of our system plus P multiplied by change in V. And let's call this equation 2I. Now, because we're dealing with an ideal gaseous system, an ideal monatomic gaseous system, the change in internal energy is equal to 3 times N times R times change in T divided by 2. Now, notice because we assume that in both processes, the temperature increases by the same exact amount, the change in temperature is the same for both cases. And that means for both processes, the change in internal energy is also the same. So that means we can take equation I and plug equation I in.
Wait, he didn't. Oh, get out. So I thought he's going to derive this. Since for an ideal monoatomic gas, NR delta T. So I still don't know how he got it. We have to keep going back. For any ideal gas, since delta internal is 3/2 NR delta T, so he still didn't derive it. Keep going back. Delta internal 3/2 NR delta T. Did he derive it? I don't think so. PV equals nRT. P equals nRT. nRT natural log.
We are often asked to calculate the amount of work that is done in a certain process. Now, as of now, we spoke about 3 different types of processes. We spoke about isothermal processes, isovolumetric processes, as well as isobaric processes. In this lecture, we're going to calculate the amount of work that is done by the ideal gas in each respective process. Now, we're also going to see that the amount of work done in a process does not only depend on the initial and final conditions, but it also depends on the pathway taken. In other words, it depends on the type of process that we are using. So let's begin by looking at the following system. Let's suppose that we have a system of ideal gas molecules shown by the following orange dots. So these are our ideal gas molecules. And let's suppose that the surroundings include the piston, the container, and everything else.
This is just an example. How does he have this? Delta energy internal is 3/2 NR delta T. Where does this come from?
So let's look at the following example. Suppose that an ideal gas system is slowly compressed at a constant pressure of 5 atms from a volume of 25 liters to a volume of 5 liters. And during this process, energy flows out of our volume is equal to, well, the pressure is 5 multiplied by 100 out, and we find. Now, let's move on to the second process. Because the volume remains constant, the small change dV is also equal to 0 joules or 0 kilojoules. And that essentially means from point 1 to point 2 and joules. So this is how. Now let's move on to part B. Calculate the total heat flow into our gaseous system. So in the beginning, we said that point 1 and point 3 lie on the same exact isotherm. And that means that the temperatures are exactly the same at point 1 and point 3. So because when we go from point 1 to point 3 via this pathway, because the temperature is the same exact value at point 1 and point 3, there is no change in temperature. And so our internal energy of our system remains constant. So because the change in internal energy is equal to this quantity, the product of 3 divided by 2 times N times R times change in T, and because the change in T is 0, the change in internal energy is also 0. And from the first law of thermodynamics, we know that the change in internal energy of our system.
Okay, I don't know where he's getting it from. Can't really. This is so difficult. So E equals 3/2 NR delta T. Okay, we just have to continue searching. So E equals 3/2 NR dt. Something like that. No, they're not. So instead of dt, we have to go to delta t. 3/2 nRT.
Ke, the kinetic energy of a single particle, Ke, is equal to 1/2 mass times velocity squared.
Mm-hmm.
I've made a video on the derivation of that. And if you haven't already seen that video, there's a link down below, and you might want to do that. It will make watching this video much clearer. So what we're going to do is we're going to put a particle. See if I can draw one. We're going to put a particle in a box. The box is going to have sidewall S. You think of it as cubical as you want. For later, we are going to use that. But a particle in a box of sidewall S. And what we want to talk about is the velocity component of our particle. And the velocity of our particle, suppose it's in an X, Y, Z direction. So it has an X component, a Y component, a Z component. We're principally going to be concerned with the X component. So our particle will move this way. It'll move in the X direction. It'll collide with the wall. It'll turn around and go back, collide with the other wall. It'll come right back to where it is. So we can talk about the momentum of the particle, delta P. And the momentum of the particle is going to be 2 times the mass times the X component of the velocity. Now, this is just for the one particle. And the reason it's 2 times that is it makes a complete circuit. It's a part of the circuit, one full wall distance, and then back again. And so that's how we get to 2mx. Now, in terms of the time that it takes for it to
Wait, what is delta P?
go there, it's momentum will move in the X direction. It'll collide with the wall. It'll turn around and go back, collide with the other wall. It'll come right back to where it is. So we can talk about the momentum of the particle, delta P. And the momentum of the particle is going to be...
Delta P is not the momentum of the particle. Delta P is a change in momentum.
2 times the mass times the X component of the velocity. Now, this is
What? Jesus Christ. This says that the change in momentum, well, momentum is mv, but there's no v here. The change in momentum is mv. Change in momentum is in mv units. M is here, but this is not v, this is L. This is some length. So the units are wrong.
So in this video, I'll basically be deriving this expression. But before I get into the derivation of this expression, I need to explain some background information regarding how we arrived to this expression coming up. Think about the real gas. A real gas has randomly moving particles whose average velocity gives us the measure of the kinetic energy, and it also has intermolecular forces of attraction between the molecules. The measure of the intermolecular forces of attraction gives us the potential energy of the gas. So as far as a real gas is concerned, when we add the potential energy and the kinetic energy together, we get what we call the internal energy of the gas. We discussed this concept in a previous session when we were trying to explain the first law of thermodynamics. Now, if I may speak about a real gas, we have oxygen, carbon dioxide, nitrogen, and so forth. These gases have different behavioral characteristics, and so it becomes a bit tricky to get one single equation that can be used to deal with all of them. Now, this is where the ideal gas comes in. What is an ideal gas? An ideal gas is simply a theoretical. So in this video, I'll basically be deriving this expression. Now, here's one thing about the real gas. A real gas has randomly moving particles whose average velocity gives us the measure of the kinetic energy, and it also has intermolecular forces of attraction between the molecules. The measure of the intermolecular forces of attraction.
Intermolecular attraction? Oh my god.
How to derive Cp minus Cv is equal to R for an ideal gas. Now, what is Cp? So in this video, I'll basically be deriving this expression. But before I get into the derivation of this expression, I need to explain some background information regarding how we arrived to this expression coming up. Now, in our previous sessions, we discussed the first law of thermodynamics, and in this, we were able to illustrate using the real gas. Now, here's one thing about the real gas. A real gas has randomly moving particles whose average velocity gives us the measure of the kinetic energy, and it also has intermolecular forces of attraction between the molecules. The measure of the intermolecular forces of attraction gives us the potential energy of the gas. So as far as the real gas is concerned, when we add the potential energy and the kinetic energy together, we get what we call the internal energy of the gas. We discussed this concept in a previous session when we were trying to explain the first law of thermodynamics. Now, if I may speak about a real gas, we have oxygen.
Okay, I need to watch it. Where I need a link to something. Okay. So we need thermodynamics. Thermodynamics.
this way. In general, the first law of thermodynamics here, we are trying to relate the principle of conservation of energy to how heat supplied into a system relates to the internal energy and work done. Now, by a system, I mean a system, a gas. This right here is a pot. Let's assume inside this pot we have a gas. Of course, a gas has got those kinds of molecules. Now, when we administer heat into this gas, the relationship that exists between this heat being administered to this gas and the effect that follows as a consequence of this heat being delivered to this gas, the consequence here being the work done by this gas, is what we are calling the first law of thermodynamics. And in a way, you see that we are having this heat being converted into this gas, being taken up by this gas. And the relationship here has something to do with conservation of energy. Now, the law of conservation of energy, if you may already know, states that energy is neither created nor destroyed, but it can be transformed from one form to another. So when it comes to the first law of thermodynamics, this is exactly what we are trying to illustrate. This is heat. This heat is heating up the gases, these particles inside this. Now, of course, we know that these particles in between here have got what we call intermolecular forces of attraction. These intermolecular forces of attraction between these molecules in this pot of this gas are what are giving us the measure of the potential energy in these particles. Of course, if the intermolecular forces of attraction are weak, it means that these molecules will be far apart. When the intermolecular forces of attraction are strong, these molecules will be close enough. Now, these molecules, because it's a gas, they are always constantly moving and hitting the walls of this pot. And because they're constantly moving and hitting the walls of this pot, they do so by some velocity. So this velocity of these particles gives us the measure of the kinetic energy. So when we look at a system like this one, we are seeing that these molecules have what we call both potential energy and kinetic energy. Now, when we add the potential energy to the kinetic energy, or if I may say, the summation of the potential energy and the kinetic energy is what is giving us what we call the internal energy of this gas. So in other words, the internal energy of this gas is simply the summation of the potential energy and the kinetic energy of the particles of this gas. So we shall be referring to the...
This doesn't make any sense. I don't know what forces exists between molecules. This makes no sense. I've never heard of this. I don't know what to do now. We have to keep looking. We just have to keep looking for there's no P. P. We need to say that energy is equal to 3/2 nRT. Let's start with that.
I've already told you multiple times that big uppercase U is the internal energy of a system. And it's really everything thrown in there. It's the kinetic energy of the molecules. It has the potential energy if the molecules are vibrating. It has the chemical energy of the bonds. It has the potential energy of electrons that want to get someplace. But for our sake, especially if we're kind of in an introductory chemistry, physics, or thermodynamics course, let's just assume that we're talking about a system that's an ideal gas. And even better, it's a kind of monoatomic ideal gas. So everything in my system are just individual atoms. So in that case, the only energy in the system is all going to be the kinetic energy of each of these particles. So what I want to do in this video, it's going to be a little bit of mathy, but I think it'll be satisfying for those of you who stick with it, is to relate how much internal energy there really is in a system of a certain pressure, volume, or temperature. So we want to relate pressure, volume, or temperature to internal energy. Notice, all the videos we've done up until now, I just said, what's the change in internal energy? And we related that to the heat put into or taken out of the system, or the work done to or done by the system. But now let's just say, before we do any work or any heat, how do we know how much internal energy we even have in a system? And to do this, let's do a little bit of a thought experiment. And there is a bit of a simplification I'll make here, but I think you'll find it okay or reasonably satisfying. So let's say, let me just draw it. I have a cube. And something tells me that I might have already done this pseudo proof in the physics playlist, although I don't think I related it exactly to internal energy. So I'll do that here. So let's say my system is this cube. And let's say the dimensions of the cube are x in every direction. So it's x high, x wide, and x deep. So its volume is, of course, x to the cube, x to the third. And let's say I have n particles in my system. N, capital N particles. I could have written lowercase n moles, but let's just keep it straightforward. I have n particles. N particles, so they're all doing what they will. Now, this is where I'm going to make the gross simplification, but I think it's reasonable. So in a normal system, every particle, we've done this before, just bouncing off in every which way, every possible random direction. And that's why, when they ricochet off of each of the sides, that's what causes the pressure, and they're always bumping into each other, et cetera, in all random directions. Now, for the sake of simplicity of our mathematics, and just to be able to do it in a reasonable amount of time, I'm going to make an assumption. I'm going to make an assumption that 1/3 of the particles are going, well, 1/3 of the particles are going parallel to each of the axes. So 1/3 of the particles are going in this direction, are going, I guess we could say left to right. 1/3 of the particles are going up and down, so are going up and down, 1/3. And then 1/3 of the particles are going forward and back. Now, we know that this isn't what's going on in reality, but it makes our math a lot simpler. And if you actually were to do the statistical mechanics behind all of the particles going in every which way, you would actually end up getting the same result. Now, with that said, I'm saying it's a gross simplification. There is some infinitesimally small chance that we actually do fall onto a system where this is already the case. And we'll talk a little bit later about entropy and why it's such a small probability. But this could actually be our system, and this system would generate pressure, and it makes our math a lot simpler. So with that said, let's study the system. So let's take a sideways view. Let's take a sideways view right here. And let's just study one particle. Maybe I should have done it in green. But let's say I have one particle. It has some mass m and some velocity v, some particle right there. And what I'm curious, and this is one of the capital N particles in my system, what I'm curious is how much pressure does this particle exert on this wall right here? on this wall right here. We know what the area of this wall is, right? The area of this wall is x times x, so it's x squared area. How much force is being exerted by this particle? Let's think about it this way. It's going forward or left to right just like this, and the force will be exerted when it changes its momentum. I'll do a little bit of review of kinetics right here. We know that force is equal to mass times acceleration, when we know acceleration can be written as, which is equal to mass times, I'll just write change in velocity over change in time. And of course, we know this could be rewritten as, this is equal to mass as a constant, doesn't change, and for the physics we deal with, so it's delta, we could put that inside of the change, so it's delta mv over change in time. And this is just change in momentum, right? So this is equal to change in momentum over change in time. So that's another way to write force. So what's the change in momentum going to be for this particle? Let's gonna bump into this wall. We're in this direction right now. It has some momentum. Its momentum is equal to mv. Then it's going to bump into this wall, and we're going to ricochet straight back. And what's its momentum going to be? We're going to have the same mass and the same velocity. We'll assume it's a completely elastic collision. Nothing is lost to heat or whatever else. But the velocity is in the other direction. So the new momentum is going to be minus mv, because the velocity has switched directions. Now, if I come in with a momentum of mv, and I ricochet off with a momentum of minus mv, what's my change in momentum? My change in momentum off of that ricochet is equal to, well, it's the difference between these two, which is just 2mv. Now, that doesn't give me the force. I need to know the change in momentum per unit of time. So change in momentum per unit of time, So how often does this happen? How frequently? Well, it's going to happen every time we come here. We're going to hit this wall, then the particle's going to have to travel here, bounce off of that wall, and then come back here and hit it again. So that's how frequently it's going to happen. So how long of an interval do we have to wait between the collisions? Well, the particle has to travel x going back. It's going to collide. It's going to have to travel x to the left. This distance is x. Let me do that in a different color. This distance right here is x. It's going to have to travel x to go back. It's going to have to travel x back. So it's going to have to travel 2x distance. And how long will it take it to travel 2x distance? Well, the time, delta t, is equal to, we know this, distance is equal to rate times time. Or if we do distance divided by rate, we'll get the amount of time we took, right? This is just our basic motion formula. So our delta t, the distance we have to travel, is back and forth. So it's 2x's divided by, what's our rate? Well, our rate is our velocity, divided by v. There you go. So this is our delta t right here. So our change in momentum per time is equal to 2 times our kind of incident momentum, because we get ricocheted back with the same magnitude but negative momentum, so that's our change in momentum. And then our change in time is this value over here. It's the total distance we have to travel between collisions of this wall divided by our velocity. So it is 2x divided by v, which is equal to 2mv times the reciprocal of this. So times is just fraction math. V over 2x. What is this equal to? The 2's cancel out. So that is equal to mv squared over x. Interesting. We're getting someplace interesting already. And if it doesn't seem too interesting, just hang on with me for a second. Now this is the force.
Let me just make sure. This is really interesting. It's a very interesting derivation. So 2mv over 2x, the 2 drop out. The v squared. The x stays, yeah. So it's mv squared over x.
Force being applied by one particle is this force from one particle on this wall. Force from particle. Now, what was the area? We care about the pressure, right? The pressure. We wrote it up here, right? We wrote the pressure is equal to the force per area, right? So the pressure is equal to the force per area. So this is the force of that particle. So that's mv squared over x divided by the area of the wall. What's the area of the wall?
X.
The area of the wall here. Each side is x, and so if we draw the wall there, it's x times x, it's x squared. So divided by the area of the wall is x squared. Now what is this equal? This is equal to mv squared.
It's mv squared. So the x squared goes on top, so it's times x.
Squared over x cubed, right? I just divide.
Oh, wait, what? Okay.
Just say this is times 1 over x squared. This all becomes x cubed. This is just fraction math. So now we have an interesting thing. The pressure due to this one particle, pressure from one particle, let's just call this from the particle, from this one particle is equal to mv squared over x cubed. Now what's x cubed? That's the volume of our container over the volume. I'll do that in a big, V, right? So let's see if we can relate this to something else that's interesting. So that means that the pressure being exerted by this one particle.
Pressure times volume is energy. So energy is mv squared.
Well, actually, let me just take another step. So this is one particle on this wall, right? This is from one particle on this wall. Now, of all the particles, we have n particles in our cube. What fraction of them are going to be bouncing off of this wall? They're going to be doing the exact same thing as this particle. Well, I just said 1/3 are going to be going in this direction, 1/3 are going to be going up and down, 1/3 are going to be going in and out. So if I have n total particles, n over 3 are going to be doing exactly what this particle is going to be doing, right? So if I wanted, this is the pressure from one particle. If I wanted the pressure from all of the particles on that wall, so the total pressure on that wall is going to be from n over 3 of the particles. The other particles aren't bouncing off that wall, so we don't have to worry about them. So if we want the total pressure on that wall, I'll just write.
Wait, the total pressure? Well, the total number is n, so it's n over 3.
Pressure on the wall. Total pressure on the wall is going to be the pressure from one particle, mv squared, over our volume, times the total number of particles hitting the wall. So times
capital N, but only 1/3 are hitting this wall.
Times the total number of particles is n divided by 3, because only 3 are going to be going in that direction. So the total pressure on that wall is equal to mv squared over our volume of our container times the total particles divided by.
You said only 3? Only 1/3.
mv squared over our volume times the total number of particles hitting the wall. So times the total number of particles is n divided by 3, because only 3 are going to be going in that direction. So
because only 3. No, only 1/3. This is at 11:47. No one caught it.
The total pressure on that wall is equal to mv squared over our volume of our container times the total particles divided by 3. Let's see if we can manipulate this thing a little bit. So if we multiply both sides by, let's see what we can do. If we multiply both sides by 3, 3v, we get PV times 3, right, is equal to...
Okay. Is equal to NMV squared.
mv squared times n, where n is the number of particles. Let's divide both sides by n. So we get 3.
So we're going to divide by n. So 3PV over n is equal to mv squared.
PV over. Actually, no, let me leave the n there. Let's divide both sides of this equation. Let's divide both sides of this equation by 2. So we get, what do we get? We get 3 halves PV is equal to, now this is interesting, it's equal to n, the number of particles we have, times mv squared over 2. Remember, I just divided this equation right here by 2.
But mv squared over 2 is the kinetic energy of the particle, of a single particle, and mv squared over 2 is the total kinetic energy of the system.
To get this. And I did this for a very particular reason. What is mv squared over 2? mv squared over 2 is the kinetic energy of that little particle we started off with. That's the formula for kinetic energy. Kinetic energy is equal to mv squared over 2. So this is the kinetic energy of one particle.
Wow, it was so worth it to find this one video, to hear this analysis. Wow. So this is just statistical mechanics. This is thermodynamics. Wow.
Right? So this is kinetic energy of one particle. Now, we're multiplying that times the total number of particles we have, times n. So n times the kinetic energy of one particle.
So it's the kinetic energy of the system, of all the molecules, of all the particles.
Well, it's going to be the kinetic energy of all the particles. And of course, we also made another assumption, I should state, that I assumed that all the particles are moving with the same velocity and have the same mass. In a real situation, the particles might have very different velocities. But this was one of our simplifying assumptions. So we just assume they all have that. So if I multiply n times that, this statement right here is the kinetic energy of the system. Kinetic energy of the system. Now we're almost there. In fact, we are there. We just established that the kinetic energy of the system is equal to 3 halves times the pressure times the volume of the system. Now, what is the kinetic energy of the system? It's the internal energy, because we say all the energy in the system, because it's a simple ideal monoatomic gas, all of the energy in the system is in kinetic energy, right? So we could say the internal energy of the system. The internal energy of the system is equal to, that's just the total kinetic energy of the system, is equal to 3 halves times our total pressure times our total volume. Now you might say, hey Sal, you just figured out the pressure on this side. What about the pressure on that side and that side and that side and on every side of the cube? Well, the pressure on every side of the cube is the same value. So all we have to do is find in terms of the pressure on one side, and that's essentially the pressure of the system. So what else can we do with that? Well, we know that PV is equal to nRT, our ideal gas formula. PV is equal to nRT, where this is the number of moles of gas. This is the ideal gas constant. This is our temperature in Kelvin. So if we make that replacement, we'll say that internal energy can also be written.
So PV, so we can replace nRT over there.
As 3 halves times the number of moles we have times the ideal gas constant times our temperature. Now, I did a lot of work and a little bit of mathy, but these results are, one, interesting because now you have a direct relationship. If you know the pressure and the volume, you know what the actual kinetic, you know the actual internal energy or the total kinetic energy of the system is. Or if you know what the temperature and the number of molecules you have are, you also know what the internal energy of the system is. There's a couple of key takeaways I want you to have. If the temperature does not change in our ideal situation here, if the temperature does not change, if delta T is equal to 0, if this doesn't change, the number of particles are going to change, then our internal energy does not change as well. And so if we say that there is some change in internal energy, and I'll use this in future proofs, we could say that that's equal to 3 halves times nR times, well, the only thing that can change, not the number of molecules or the ideal gas constant, times the change in T. Or it could also be written as 3 halves times the change in PV. We don't know if either of these are constants. We have to say the change in the product. Anyway, this was a little bit mathy, and I apologize for it, but hopefully it gives you a little bit more sense that this really is just a sum of all the kinetic energy. We've related it to some of these macro state variables like pressure, volume, and time. And now, since I've done the video on it, we can actually use this result in future proofs, or at least you won't complain too much if I do. Anyway, see you in the next video.
So what is the next video? That's one of the biggest problems with YouTube videos, that you really cannot learn easily. Oh, watch the next lesson. There it is.
Let's start with our classic system that I keep using over and over again, and that's because it tends to be very useful for instruction, and it also tends to be the system that is most covered in classrooms, so hopefully it'll be productive for you in your schoolwork. So I have this container. It has a movable piston on top, or kind of a movable ceiling, and on top of that, well, of course, inside of my system, I have a bunch of molecules or atoms bouncing around, creating some type of pressure on the system. So it has some pressure P1, this volume right here.
1 second. So it says here, watch the next lesson. Missed the previous lesson. This is the previous lesson. PV diagrams and expansion work. Okay, I gotta go. Let me see. We've been here for 1 hour. Okay, it's okay. So I'll see you next time.